Dan, thank you very much. Pleasure to be back at Mile High, and what a conference it is. So many people, so many friends. Thank you for coming. So today talks is about improving ABR encoding by adaptation to true resolution of the content. I'll explain what we call true resolution, and the talk is with several of my colleagues for many years, Carol Lillewald, Abhijit Jagannath, and Nabajit Barman. Abhijit and Nabajit are attending the conference. Say hi if you see them. And let me start. So the problems that we're addressing is actually nothing new in modern days video delivery. Workflows for pushing video in broadcast and then OTT become increasingly complex, and we have many points at which content could be transcoded or converted. And such conversions might include addition of noise by transcoding, of course, and they might in some cases involve changes of resolution. Some cases we downscale content, and remarkably enough, in some cases we also upscale content before it goes to distribution. And obvious cases include, of course, conversions between standard formats, SD to HD, but then there are other cases which are more interesting. For example, working with widescreen content and converting it to 16:9 also sometimes includes upscaling. And why it is bad? Of course, if content is upscaled, we have more pixels, and we need to use more bits. But the result doesn't look any more sharper. So the system becomes less efficient. And to explain this at some level of visual examples that I hope will be appreciable, let me show this content. This is, of course, well-known Tears of Steel sequence, which comes as a widescreen content. 2.4 to 1 is the display aspect ratio. It has only 800 pixels vertically. And what happens if I will try to convert it to 16:9? I will chop the midsection, scale it, and it will become 1080p. With one caveat, that the true resolution at this point will be only 1422 by 800 pixels, because the original vertical height was 800 pixels. So I effectively blown number of pixels, but I didn't increase the spatial richness of the content. And why is this as bad? What are the effects? So if I now try to encode this content, and I use classical per title or CAE type of tool to encode it, I see that I'll produce a ladder. I will use about 3.7 megabits at the top bitrate rendition, about 8 megabits total. And it all looks okay, but what if I do it differently? What if I just stop ladder at the true resolution? If I know that the true resolution is about 800 pixel height, why wouldn't I just chop the ladder earlier? And if I do that, we see that the number of bits could be reduced. SSM is about the same, but now we use 2.5 megabits instead of 3.3. The storage is also much lower. So in fact, this naive and simple example shows that there is already 26% of bandwidth that could be lost right on the flat surface if you do things in a straightforward manner. And things like this do happen left and right, and with modern days 4K workflows, we see lots of 1080p content being up converted to 4K. Of course, in that case, the loss of efficiency is much more profound. We're talking about factors of 2 or 3 increase in bandwidth with no meaningful improvement in quality in most of cases. And what also is bad about downscaling and then upscaling the content? Well, you might actually affect artistic content. So in this case, I show the example of content. It's from movie Safe House, where one person is holding a hand of another who is dying, and the artist added this very sharp noise to dramatize this content. Of course, if you downscale, upscale it, now it looks softer. You don't have same emotional aspect with it. So there are all sorts of other problems coming with downscaling and upscaling, and how to work with this. What solutions exist today to to try to mitigate the effects of those conversions? Well, if we talk about just compression efficiency, there are, of course, for title, content-aware, context-aware techniques, which kind of work. If content is upscaled, it becomes more compressible. And so CAE type of techniques will allocate fewer bits to an upscaled content. You will be able to increase efficiency somewhat, but not completely, because they will still have more pixels. And as we've shown in previous example, you might still overspend bits. And importantly, the number of your streams will still be larger. You need to go all the way to the top resolution, so you probably will have more streams there. So they help, but they don't help completely. The other classes of technique is so-called dynamic resolution encoding. And this is something that is standard nowadays in VVC. Within the stream, you could allow encoder to dynamically downscale content and then upscale. And this is typically done as part of encoder internal logic, as part of RD optimizations. But as I've shown earlier, this is not always safe. If you have content with film grain, it might change artistic content. It might introduce some negative effects. So, and fundamentally, it's still not going to change the number of streams. So it helps somewhat, but not completely. But then there are classes of techniques that are known as true resolution detectors. It's been coming from a completely different field. They've been used in forensic analysis, forgery detection. These are signal processing tools designed to detect if image become upscaled. And some of these detectors are super effective for dealing with specific type of filters. For example, classic Gallacher's technique works very well with bicubic filters. If you use bicubic subsampler, it will detect with high probability that this was the true resolution, but it's not going to work with other filters. And very few of these techniques work with super resolution upsampling, and they're not always, so there are many of them, but they come with some caveats. But overall, looking at the space of the solutions, we feel that picking one of those forensic analysis tools would actually be quite useful for addressing the problem. And how we propose to address it, and by the way, this is the flow diagram of something that's already in product in Breitkopf CAE, context-aware encoding. What we did, we added a true resolution detector in front of the CAE ladder generator. So what it does is this tool effectively analyzes the content. It detects what is most likely true resolution that was there, if it was upscaled. If it wasn't upscaled, everything works as is. But if it detects that the content was upscaled, it effectively pushes that information to CAE as a limit to the maximum resolution to include in the encoding profile. So if ladder will be generated, it will stop at, for example, 800 lines. It's not going to go to 1080 if the content was upscaled. And the rest of workflow is the same. We also have control logic to enable operators to do it safe. For example, some operators will only want to know that content got upscaled, and if that was the case, maybe they should talk to their content provider and ask them why, for example, content which we bought as HD is coming as SD upscaled. But some others would be okay with us not only detecting, but also limiting the profile, at which point it goes and encodes the content most efficient fashion. So this cascade is easily grasp enables us to reduce number of streams, reduce the resolution to meaningful maximum that there is there, and appreciate all other savings. So now let me talk about the resolution detector that we designed. It's actually pretty straightforward. So what we do is we split video in lines and columns and use fully separable processing. It's all Fourier domain processing. We extract spectral features in horizontal vertical domains. Then we detect few candidate resolutions horizontally and vertically, and then we fuse them in final block by looking at consistency checks with SARs and DARs, and I'll pick final combinations that comes with best overall scores altogether. The unique feature of this is that we also use estimate of codec noise as one of the parameters for our classifiers. And I'll explain why this is important later and how we estimate codec noise. Very simple. We parse the mezzanine, we look at QPs, frame types, and this is a very well-known class of techniques, paper of Eden of, I think, 1990s, and several following explained how to do it. But then let's look what goes inside. And the key here is spectral features that we're using. And to talk about spectral features, I'll need to bring a bit of a background. And this is all classical signal processing. So when we generally work with rescaled content, there are at least two filters that are involved in this process. There is a first filter that was applied before sampling, and there is another filter that is applied after the sampling to reconstruct it. And these filters, of course, according to Shannon and Nyquist, supposed to be sync filters to achieve perfect rejection, but none of the practical filters is perfect. And I'm showing responses of family of Lancaster filters. Of course, they have not perfect rejection, and they have all sorts of ripples in rejection bands. And what this all means, that if you apply practical filters either before or after sampling, we will have aliasing artifacts, and they will have two types of them, in fact. The first kind is coming from a situation where the pre-filter was insufficiently sharp, and there is an overlap between main image spectra and adjacent image spectra, and that creates aliasing. And the other one, which is less frequently recognized, is a case where, well, your pre-filter was perfect, but then your reconstruction filter might end up being too broad. And that turns out also generates aliasing artifacts, and they both look very similar. And this example comes, in fact, from paper of Netravalli and Mitchell of 1980s, a classical paper, very much recommend. So bottom line here is all practical images, if they rescaled, they come with some aliasing artifacts. We may see them, we might not see them, they might be sufficiently suppressed, but they're still there, and this is something that we can use as basis for our detector. And here is the principle of our detector system. So effectively, we work in a spectral domain. Fn is the Nyquist frequency, Fc is our candidate cutoff frequency, and then shaded regions are energy before cutoff and after cutoff. And then we have two metrics. One is a measure of aliasing that we use around Fc, and the other is a measure of power decline in the vicinity of Fc. And they both are used as indicators that Fc is likely the original cutoff frequency. And then the energies are used together with mezzanine noise to bound the cases. So what we enforce is that the energy of that portion of the spectrum that we're about to throw out is sufficiently small in absolute and relative sense. And now to detect aliasing, we use very simple metric. It's just a normalized correlation coefficient in imaginary spectrum. So we just fold spectrum around Fc left and right and compute it. And what happens at the bottom, I'm showing this same image, which was true resolution 800 pixels vertically and scaled to 1080. And this is the imaginary spectra, and the plot shows how this metric resonates around each point. And we see that at Nyquist midpoint, it resonates the most. That's where the spectrum becomes perfectly antisymmetric, because that's a property of spectra of real values. It's conjugate symmetric in the Fourier domain. And so at this point, our anti-correlation goes to absolute minimum, but then at the point of 400, which is a Nyquist of 800 pixels vertical, it's also resonate down, but to somewhat lesser extent. But we still can pick it. And by the way, if the image was rescaled several times, we will have several of those dips along the spectral line, and this is how we know that these are the likely frequencies at which image was originally sampled. And together with spectral decline in power, we use this as indicators that this is likely the point at which the signal was sampled. And with this, I will just show some experiments. results. So we use test corpus of about 500 items to test it, and massive corpus, real-world content, and we computed cases when we use a regular standard ladder versus CAE ladder, and then CAE ladder with resolution detector added on the top of it. And these are the results. So this is what we see. And again, this is a real-world mezzanine that we gathered from production. We see that overall, of course, CAE gives very significant savings by itself, but if we add true resolution detector, we see extra savings and quite meaningful. In a number of streams, we see about 2%, 2.5, then we see about 11% savings in storage and about 9% savings in bandwidth. And this is overall across all these 500 mezzanines. If you look specifically at different categories, in some cases, savings go up to 30%. And if you look at per asset basis, we see some cases savings could be 80% also. So it's a meaningful tool overall. We see that it adds to the efficiency quite a bit. But what this also means? Well, it also means that this is quite alarming. It means that there are lots of upscaled content out there. And the more complicated workflows will be in the future, the more cases of upscaled content being pushed for distribution will be present with 4K, 8K. I'm sure there will be more of this. And we believe that true resolution detector and detection types of techniques will be increasingly commonly used tools used in media processing workflows in the future. So with this, thank you very much.